class. That is question number 2. And the next class, guess what we're going to do? That's question 3. And you're probably thinking, Mr. Seals, where's question 1 at?
We don't go over it.
Question 1 was what we did before spring break when we had electric fields and magnetic fields perpendicular with an object moving in a straight line.
That's so easy. Oh, so y'all are skipping 4.
So I'm telling you directly what we're going over and which free response question it's over. We got that?
All the books.
Okay.
I'm gonna return some of these to the library. How could they?
All right. Oh, man. Oh, okay, guys. Hey, back in October, we learned about something called the right-hand rule, and that currents create magnetic fields. And we had a wonderful equation, and we were all happy with this equation. This was a great equation. Everyone loved this equation. It was B is equal to mu I over 2 pi r. And we were all happy with that equation. And it's on the Physics 2 equation sheet. And we were all rejoiceful, and guess what? We're in Physics C and it's gone. Because they expect you to be able to derive it, but not doing the method we do today. What? How does that make sense? You can use the method we're doing today, but they only want you to set up the integral, and there must be an easier way, like we did last time. All right? So, basically, if you guys remember, we could go and solve for the electric field of a particle using k times q over r squared, right? There is an inversion of that equation for magnetism, and it's called Biot-Savart's law. This is not the version they give you on the equation sheet, but this is the, quote, official version. It is a constant times a charge times its velocity over a radius squared times a angle, and this is the angle the velocity and the radius make. Okay, this is not on the equation sheet. This is not on the equation sheet. This is just the fundamental equation. Maybe I need to verify that's not on the equation sheet. Let me go and verify that real quick. I know which one I have never seen this one ever used. That's the difference. I'm going to go and verify because Mr. Seals could be lying to y'all. Mr. Seals is probably lying to y'all. Mr. Seals is 100% correct. This version of the equation does not show up on the equation sheet.
Oh, it's the dB version that shows up on the equation.
What shows up is this dV version. Where what it is, and it actually doesn't even show up like this. The official version is, oh shoot. The official version on the equation sheet is mu 0 over 4 pi I cross
DL.
You're right. I DL cross R hat over R squared. Now I hate the DL cross R hat. I hate that. It makes no darn sense to me. You know what all that means? Sine of the angle, which is the angle the wire and the radius make. It's this angle right here. That's what you need to know. Yes? So, the r hat is what is considered a unit vector, which has an exact value of 1, and we're multiplying it by a little piece of dl, and instead of just writing dl sine theta, They decided to put the cross our hat because some physics professor out there it will confuse the kids because they will not know what angle theta is. Oh my gosh, my voice is going out already. It's day one.
Wait, what is that tiny little cylinder over there? Oh, that's the tiny
That's
wire.
a little piece of DL.
Oh, the wire, and then. Okay.
And we're finding out how much magnetic field is created by this little piece of wire at this location R. Okay? All right, we all good on that, right? Okay. So, we're always going to start off with this equation. Even though it doesn't show up on the equation sheet, they will accept this because this is kind of it equals the same thing we just talked about, right? Okay. So what we need to do is we need to figure out what is the magnetic field created by this infinitely long wire. And College Board does not expect you to solve this integral. But you know what they expect you to do? Set it up. Okay. So, what we're going to do is, starting from that first equation, there's another way I can write this. And this is equal to, mu is equal to, B is equal to mu over 4 pi, the integral of, actually it doesn't, I can pull the q out because the q is, no, we don't have a q, we have an I. Sorry, we can pull the I out because the I is constant. And what we're going to be left with is a piece of dl over r squared with the sine of theta. Now, if you notice, what dimension is this wire in? This wire in this case. And the other one, it was y, right? It's going to be x, right? So we're going to we need to replace all these values in our integral with x values. So we get to do some fun things. The first thing we're going to replace is what's dl? dx, there we go, that was an easy one. Okay, what's r squared going to equal?
D squared x squared plus x squared.
So,
X squared.
I'm going to rewrite it a different way if that's okay.
Okay.
I'm going to write it as, let's see, I'm going to write it as, actually I'll leave it like that. I don't know why I'm doing that, but we're going to go with it. X squared plus d squared, right? The last thing we have is last thing we have is sine theta.
Oh, d over r. Right?
So our sine theta has to equal d over x squared plus d squared
Square root.
to the square root. Oh no, guys. That means, I'm going to block all these off. That means that when we set up our integral, we get mu I over 4 pi, the integral of d, I hate that we have d dx, but you guys realize the two d's are different, over,
Wait, why isn't it just dx? Why is it d dx?
because we have a d right there,
Oh, that's okay.
over x squared plus d squared to the 3. Oh gosh, that 3 halves showed up again. I am so sick and tired of that 3 halves, right? And now we got to put our limits of integration on this one, right? So because it's an infinite wire, it would go from negative infinity to positive infinity. What if it's a finite wire?
One x to the other x.
Yeah, one side of the wire to the other side of the wire. And it would work even if it's an asymmetric wire. All right? This is the setup. You need to know to go and convert these things into these things. Okay?
That's actually not that bad.
It's not that bad because we've done it before.
Yeah.
That's why we have the stupid 3/2 show up again. Okay, so let's see. Did I do it all right? Yes, I did it all right. Yay! Now, do we need to know actually how to solve this integral? No, we just have to set it up.
Yeah, I really don't feel like doing this.
But I can just tell you if we plug this into a integral evaluator, hey look, there's the equation we like so much.
Oh, wait. Our darling, our beautiful.
Now I'll show you an easier way of getting this equation next time. Okay,
We love, okay.
so everyone's happy with this, right? Okay, so that's for an infinite wire. What other shapes does College Board expect you to know how to deal with?
It's an arc. Oh.
It's an arc.
Okay.
Now actually before we do
PTSD.
anything, can I go and give you like a quick extra shape? Even though I don't have the slideshow, I want to help you guys out real quick. So I'm just going to do it very quickly, and I'm going to do it underneath here. Is that okay? Because I have the equation, my favorite little equation right here. This is the form I like it in. This is the form I like it in. And I'm going to do it really quickly right here. And it's going to be, here's a point, here's our point, right? Our point P. And we're going to have a line that is sideways, right? Okay? What angle does the radius and the little piece of DL make? 0. What sign of 0? So the magnetic field at this point is equal to 0.
Oh.
If a wire is parallel with the radius, so basically if this wire will go through point B if you extend it out infinity, it will create no magnetic field.
Oh.
That is actually one of your quest questions, by the way.
Nice.
Okay, so let's talk about this arch real quick, right? So hey, we got to go and replace, so we're going to look at our arch right here, we got to replace our DL with something, right? Well, if you remember back when we did electricity, notice the radius is a constant, right? So we can pull it out of the integral. So we get is B is going to equal mu 0 over 4 pi r squared. I is also a constant. And now we have an integral with DL and sine, but our sine of our angle, but notice what our angle is on this arch.
Sine 90, which is 1.
Which is 1.
Nice.
So that means we're just integrating DL.
Oh, and that can be 2 pi r over whatever angle. The one between the arc, wire, yeah.
So what we're doing is we're integrating the length, adding the length of this wire. Now, hopefully we remember how arc lengths work. And you guys will agree that this is just theta times r.
Oh. I overcomplicated.
So what's great about this, you don't even have to evaluate the integral. If it's an arch like this, you just have to write down the arc length on this side. This DL sine theta just becomes our arc length. So this ends up equaling mu I over, there's a theta here, 4 pi r.
This is really not that bad.
This is not bad at all. What if yeah.
How do you know it's sine equals 90?
Because remember, the angle inside of this integral, that angle right there, is not talking about this angle, this arc length right here.
Oh, so it's
This angle is the angle the radius and DL make. Yeah.
What would be the equation if it wasn't at this side?
If it wasn't at the center? Oh. Then our radius would be changing distances as we go around the arch. And we'd have to go and it would be a pain. That's all I'm just going to say. College Board is never there. I'm going to tell you the two situations you have to know. You have to know an arch where you're in the center of the arch or center of the circle or a line. Those are the two situations they expect you to know. That's it. Does that kind of make sense? So, I did kind of miss something for you guys real quick. This tells us the value, right? How do I figure out what direction the magnetic field is at point P?
Can you not use the right hand? Okay, so the current's going like that.
Okay, wrong right hand rule. The current is going this way, right? Which way do my fingers wrap on this way around this arch? So these would be a dot located in the center.
Oh.
Does that kind of make sense? Wait, if you guys remember when we did electric fields, if we had an arch that went all the way around, it would have 0 in the center, right?
This way.
Is it 0 in the center if it goes all the way around?
No.
Oh, look.
Keep going up.
It comes out in all directions. Which makes sense because when we plug in our value of beta equals 2 pi, we get a constant value there. Now, hey guys, you want to know what the hardest question on your quest is? So basically, I want to give you guys time to go and do quests today. I get the first 10 questions. Now I'm going to tell you, this quest is a pretty easy one because half of the questions are multiple choice ones.
My guessing skills will come in.
Now, the hardest question is this arch?
What is that?
Hey, we're doing CPR today.
It is a loop that has an inner arch, an outer arch, and 2 lines that go outwards.
Huh?
Good luck.
Who's that guy?
Farmer, what are you doing here?
Let's do the easy ones first.